Learning Outcome 9.5. Given the Laplace transform and the ROC, find the proper inverse Laplace transform. This is for cases with complex roots. If you look in Table 9.2, there are 4 transform pairs, numbers 11, 12, 13, and 14, which are all for cases where you have a second-order polynomial in the denominator, which has complex roots. This video hopefully will help you take the inverse transforms in those cases. We're going to work this through with 3 examples. First, given that x of s is 3 divided by s squared plus 4, with the real part of s greater than 0 being your region of convergence, what is the inverse Laplace transform? We'll look at the form of that polynomial. The poles are 2j and negative 2j. These are complex or imaginary. That's your indication you do not factor this denominator. You leave it as a second-order term, and we now look in the table between transforms 11, 12, 13, and 14 to find a match. Transform number 12 says that if x of s is omega 0 divided by s squared plus omega 0 squared, and your ROC is real of s greater than 0, that your inverse transform would be sine of omega 0 t times u of t. Well, that looks like a pretty good match. You need to figure out what is omega 0. Well, if omega 0 squared is 4, there's omega 0 squared, then we know that omega 0 is 2. We're almost there. Unlike the first order denominators, the numerator has to have a specific value. That's not 1. That numerator has to have a value of 2, it has to be omega 0, which means we need to take this 3 and factor it out as 3 halves. 3 halves times 2 is 3, which gives us our original polynomial back. Now we use linearity with 3 halves, and this term fits transform pair number 12. We wind up with that as our inverse. Another example, very similar. X of s is 3s plus 5 divided by s squared plus 4. Again, real part of s greater than 0. What's the inverse Laplace transform? We saw before, s squared plus 4 gives us complex roots, and therefore we're going to look at the table, properties 11, 12, 13, and 14 for a match. We can see in transforms 11 and 12, we have that matching denominator. We see an s in the numerator, so we're going to need some amount of transform 11 and some amount of transform 12. Now you need to learn to figure out how much of each do we need to use. We know omega 0 is 2, same as in the previous example. We know we're going to need a certain amount of the s divided by s squared plus omega squared, and a certain amount of the omega divided by the s squared plus omega 0 squared. We need to look at the s term first. We've got a limited amount of s's. We know we have exactly 3 s's. Therefore, we know the coefficient that needs to go here. And now we can look at the second part. We need to have a 2 in the numerator. So what gives us 5? 5 halves times 2 gives us 5. Okay, now we can directly apply the transforms plus some linearity, and we get our inverse transform. Third example, x of s is 3s plus 7 divided by s squared plus 2s plus 5. I'm not going to tell you exactly what the ROC is, because that'll give away some of the other answers. But I will tell you this is causal, and therefore one of those 4 transforms from table 9.2 applies. Check out our poles, and our poles are negative 1 plus 2j and negative 1 minus 2j. They're complex. That means we are not going to factor this denominator and not do partial fractions with 2 first-order terms. We keep them together, and we're going to use one of the properties in table 9.2 between numbers 11 and 14. Do not factor. We're going to want to use transforms 13 and 14 for this, because these are complex and not purely imaginary roots. Now notice that both of these have a form where we have to do completing the squares. We need an s plus a quantity squared and an omega 0 quantity squared. Very quick review on completing the square. You can find other tutorials about this on the internet if you're weak on this. We want to look at the first two terms in our polynomial and say, what does that third term need to be in order to get a perfect square, and what would that coefficient need to be? Well, we know that coefficient is going to have to be half of the coefficient on the s. So that's going to be 1. Therefore, 1 squared is going to go here. We have our perfect square. That's what's going to go in this part of the polynomial. Now we need to say, all right, what do we have left over? We have our perfect square plus what will give us what we started with, give us our complete term. Well, s plus 1 quantity squared plus 4, that x has to be 4, and then we can turn that into a perfect square also. Now we know we're going to have an s plus 1 quantity squared plus 2 squared, and the numerator is going to have to be an s plus 1, and the second term, the numerator has to be a 2, has to match our omega 0. Start again with the s term first. How many s's do we have? We have 3 of them. So that means that in total, we have 3s plus 3. Plus, what do we have left over in order to get our original numerator? Well, that x is going to be 4. So that means we've got a total of 4 for the coefficients in the second term. We need a factor of 2 for our omega naught, so we have to have a 2 times a 2. Now that we've got this broken up, we can apply transforms 13 and 14 and do our inverse Laplace transform. I've got 2 more examples for you. I don't have them worked out, but I've got the questions and I've got the answers so you can work them out and see whether you can do these. Here's one example. Copy it down, don't look at the answer, and try and work it out. And here's another example you can work on. If you're successful in doing both of these, then you probably figured out what's going on. Good luck. Come ask me if you've got questions.